Welcome back to ECE 501B. Homework 3, number 3 is due on Friday. Exam number 1 is a week from today. Is that correct? That's the right date, on the 1st of October. In preparation for that, I will give you a little bit of information today, basically just quickly glide through the process that I am expecting we will follow for exam number 1 and the structure, what you can maybe expect on exam number 1. But I have now placed a sample of an exam number 1 from a year ago, and you can look at that on D2L. It has an incomplete or the blank exam, and then it has attempts at solutions to exam. So you can maybe practice on the first one and then check your work with the second. Today what I want to do is try to finish up Chapter 3. We will finish up Chapter 3 whether I am finished or not. This will complete Chapter 3. We will start by looking at maybe a different way of thinking about matrix multiplication. If you haven't thought of it in the way that I will present it, that I hope that will be useful to you. We will then talk about maps that are invertible, which means that those maps have to be both injective and surjective. If we do have an invertible map between two vector spaces, those two vector spaces are what's called isomorphic, or they are similar. They have similar features or similar elements, and then that leads us into this notion of operator, which says our input vector space is identical to the output vector space, and we are then operating from and back into the same vector space with an operator. The process for exam number 1. You will be allowed 2 sheets of notes, and you can have the front and back of those 2 sheets. So if you want to make some notes on what theorems you think are important or propositions, you can in that particular collection of notes, but that's all you will be allowed in the exam, other than a calculator, which I'm not sure you'll need a calculator, and something to write with. Yes? The notes do not have to be written by hand. You can, I guess, type those and shrink those down into microfiche, so I guess you can maybe have the entire textbook on your 2 sheets of notes, but you'll have to have young eyes to use that, and maybe you'll all notice that you're squinting or trying really hard to look at something on your notes. But I'm not going to be coming around and inspecting your handwritten notes. I think there is something to be said for actually writing it by hand, transcribing that, but if you want it to be cleaner, if you can't read your own handwriting, please feel free to do it some other way, or if you feel better with it in some other form. There's no restriction on how you use those 2 sheets of notes. That answer your question? No textbook, no classmates, no cell phone, no computer. I think that's fairly clear. The structure of exam number 1, I'm thinking there will be 5 problems, at least 1 proof. There could be 5 proofs, since I'm saying at least 1. I'm leaving the door open, but it'll probably, well, there will be at least 1 proof on the exam. You may be asked to demonstrate or show or produce counterexamples using definitions, propositions, theorems. You may be able or asked to create or build a vector space, a subspace, a direct sum decomposition, basis, matrices, injective maps, surjective maps, etc. I think the practice exam will have a problem that we won't have yet made it to. Last time I believe we were into eigenvalues and eigenvectors. We won't go there for this exam. So if you see that problem and you start sending me an email, are we having Chapter 5 on the exam? No, we're just going up through homework assignment number 3. That's the content that we will produce, and basically through chapter 3 is what I'm hoping that that allows us to do. Questions on exam number 1? Yes? Have you gotten your homework back? No, it's still in my bag. I keep thinking I'm going to do it, and then something else comes up. I thought I was going to have a grader. I haven't seen that happen yet, so I'm trying to figure out what will happen with the grading. Okay, so that, I apologize for that, but solutions I think are available, and hopefully you can sort of remember, if you didn't keep a copy of your homework, you can still sort of correlate what you think you did with the solutions. And speaking of the homework, either if I do it or if somebody else does it, the homework I treat different than the exams. The exams, I grade everything in terms of all your work. On the homeworks, that may not be the case. I may only grade 1 or 2 problems, and if you attempt the others, I'll give you credit for those. So you could get a perfect score on your homework. Don't be misled into thinking that that means you answered everything correctly. You may have completely blown problems 2, 3, and 4, which I just said I'm going to just give you all the points because you attempted it, not that you answered them correctly. And you might get all those points, and so don't just assume based on your homework score, if and when that ever happens, that it being a 10 out of 10, that you did get it all correct. Question? So that's a good question. I'm hoping it's clear from the context. The question was, am I going to indicate which problem I graded? What I will probably do is those that are attempted, I will simply put 1 out of 1 right by the number of the problem, right at the beginning. If you see marks somewhere else on your paper, you can probably assume that one may have been a graded problem. So it may not, I hope it's clear from context what is graded and what is just attempted. But if it's not, you can ask me. I'm not sure that I'm going to give you all of that information, but I hope it will be clear from the way that it's graded which one was actually graded and which ones were you given credit for just attempting. Now, getting back to matrix multiplication, we have learned how to translate linear maps into matrices. We talked earlier about this special case of how we can compose 2 linear maps. We can go from the domain space U into a codomain V, and then operate on that result with another linear map S that goes from that codomain V into from that domain V into a new codomain W, which sort of is suggesting that here is how we could treat the multiplication of linear maps. ST, that composition or multiplication on a vector V, would then be the same as S mapping the result of TV. That's what we've thought about, and that's what we talked about, and we said that that's not necessarily going to commute. ST is not necessarily going to equal TS. And then you could ask the question, how does this multiplication of linear maps work when we represent these linear maps as matrices? And that's where this script M comes in. Script M of the product of S and T, that as a matrix, it would be nice if that was equal to the matrix of S times the matrix of T. That's what we would like to have happen, and in fact that's the way it works, and we're not going to cover it. I'm assuming you can do matrix multiplication. Okay? If you stumble a little bit, go ahead and review that if necessary. but I want to maybe provide you with a way of looking at a matrix multiplication that maybe you haven't looked at or thought of in this way before. So let's say that we want to multiply two matrices. Let's say that we have now a matrix that's 3 by 3, and in the first row it's 1, 6, 4. The second row it's 5, 2, 5, and in the third row it's 7, 1, 3. And let's say that we multiply that by the first column of 1, 0, 0, 2, 0, 1, 0, minus 1, 0, 1, 1, 0, 1, 0, 2. And what I want you to maybe be clear on doing is you can actually do that multiplication rather quickly. You can say, well, that's 157. It's now, and how did I do that? Well, if you look at each of these columns as if it's operating on the matrix of columns, we now, if you look at the second matrix, I'll call that B. The first matrix is A. Here is B. The way that I was immediately able to simply write down the first column in the result is that I could see that the first column is really the result of taking 1 times the first column, 0 times the second, and 0 times the third. Meaning, I simply look at this coefficient weighting the first column, this coefficient weighting the second, and now I've run out of highlighters, but the other color of highlighter, which is empty, that 0 is scaling the third column. And in that case, all I'm doing is weighting the first column by 1, and I can immediately write down 157. If I do that for the second column, what do I need to do? I take the first column and scale it by 2, and add to that 1 times the third column, meaning the first element, or the first row of the second column, is going to be 2 times 1, 2, plus 4, or 6. The next entry is going to be 2 times 5, plus 5, or 15, and the last column, or the last row, will be 2 times 7, 14, plus 1, or I'm sorry, plus 1 times 3, 14 plus 3 is 17. Meaning we now can write down, with a highlighter, we can write down 6, 15, 17 as the second column. The third column is easy. We simply negate the middle column. We have minus 6, minus 2, minus 1. Does everybody see how this matrix multiplication works? We take the second matrix and we say each of those columns is weighting each column in the first matrix by the appropriate multiple. The fourth column in our product will just be the sum of the first 2 columns. And we can then say that's 7, 7, 8. And the last column will be 1 times 2 times the third column, or we have now 1 plus 8, or 9. We have 5 plus 10, or 15. And we have 7 plus 6, or 13. And that's now the product of A times B, and we could write that down rather quickly without having to go first row, first row, first column, first row, second column, etc. So that this particular column would have said this is negate, or the negative, of the second column of A. And you could do it just the other way. Sometimes it's easier to view the first matrix and use that as your cue. And in that case, you take the first row and you say, now I need to weight all of my subsequent rows by those scaling factors. And you would take the first row plus 6 times the second row plus 4 times the first row, or the third row. to obtain the first row in your product. That's not as clean in this case as I think multiplying or scaling the columns because of the sparsity or the numbers in the columns of B. Meaning, I want you to feel comfortable thinking about matrix multiplication as combining columns or combining rows, depending on whether you are looking at the second matrix and using the columns to then combine the columns of the first matrix, or if you're looking at the rows of the first matrix to combine the rows in your second matrix. Is that clear? Have you seen that before? Have you thought of that way of multiplying matrices before? Or is this a new thing for you? Is it new to you, doing it that way? Not too many are wanting to comment one way or the other. Let's then move on and just remind ourselves that the standard, that works for what reason? Because we have the same number of columns as rows in the first versus the second matrix. So the standard matrix multiplication maintains the properties we want. Meaning if we're given an A that's maybe m rows by n columns and a matrix B that's j rows by L columns, the product of A and B is only defined under what condition? We need n equal to j. Number of columns in A has to equal the number of rows in B. And another way of thinking of that is that's equivalent to these dimensionalities of our vector spaces that are in the domain and codomain. That's equivalent to the requirement that the output space of one map must be the input space of the other map. They have to make sense. You need to be going into your output space of the first map needs to go into the input space of your second map. The other property that you need to just be aware of, which we've talked about already, is even when the multiplication makes sense, or when the multiplications are defined, in general, the matrix of the linear map T times the matrix of the linear map associated with the linear map S is not equivalent to the reverse multiplication. A times B is not equal to B times A in general. that was for matrices where we have an A matrix and a B matrix. Your B could be specialized to just be, instead of a matrix, it could be a matrix, but it could be a column matrix or a vector, and that's still okay also. In particular, we can look at proposition pi, just seeing if you're paying attention. 3.14, proposition 3.14, suppose we're given a linear map T that takes us from the vector space V into the vector space W, and the basis on V is V sub 1 through V sub n. The basis on W is, let's say, W sub 1 through W sub n. Then the matrix of the two maps together TV is the same as looking at the matrix representation of the linear map T times the matrix representation or the vector representation of this vector V. And I guess the V is a little bit overused. V is just some representation or linear combination of the basis vectors V1 through V sub n. Questions on matrix multiplication and matrix vector multiplication. That's just what you're used to using or doing. Let's now talk about maps being invertible. A linear map T between V and W is said to be invertible if there exists a map S that goes from W to V such that ST is the identity map and TS is the identity map. So a linear map is said to be invertible if you can find, or if there exists another linear map such that ST is the identity or TS is the identity. And a map S, by definition, such that ST is equal to I and TS is equal to I, that we will say is the inverse of the linear map T. That's how we will define the inverse. And sometimes we will just write that in the common term or way as just T to the exponent minus 1. If the inverse exists, that inverse is unique, and we give it the symbol t to the minus 1. With those definitions and terms for the inverse of a linear map, we can actually now talk or introduce proposition 317. A linear map is invertible if and only if the map is injective and surjective. Means we need our linear map, if it's invertible, to be 1-to-1 and onto. If our map is 1-to-1 and onto, injective and surjective, then it's invertible, or vice versa. If it's invertible, it's injective and surjective. I will let you see the book for that proof, or maybe for a formal proof. What I would like to do is actually sort of examine this proposition from a more intuitive perspective. Examine proposition 317 intuitively. Suppose we're now given a linear map T between two vector spaces, the domain V and the codomain W. Suppose that linear map T is non-injective. What does that mean if a map is non-injective? It's not 1-to-1. What does that mean? It has a non-trivial null space, doesn't it? So now we could find vectors that actually map to the 0 vector, and we could basically add that vector to any other vector and produce a third vector, which if we operated on it with that linear map, it would go to the same spot as another vector. That's pretty wordy, but what I'm saying here is if T is non-injective, then multiple vectors in our domain V, since we have a non-trivial null space, they can map to the same point or vector in the codomain. Multiple vectors in V map to the same vector in W. Pictorially, you could have V1 and V2. You now use the map T on V1, and now you use the same T linear map on V2, and those now could go to the same vector in the codomain, W1, if we have a non-injective linear map, right? So V sub 2 could be made up of a linear combination of V1 plus a vector in the null space of T. Yes? It could be, not always, but now that it's non-injective, we know that we can have this case happening. We know that we can find multiple vectors in the domain that can be mapped into the same point in the codomain. Remember our examples from before. You could find a vector in the null space of T, and now you could add that vector to any other point in your domain to create a new vector, but that new vector, which we could call V sub 2, is going to map to the exact same place as V1 if V2 is, let's say, V1 plus a V3, where V3 is in the null space of the linear map. Is that clear? Now, with that, remember what we said about a linear map. A linear map requires a unique output for a given input. With that said, there's no way the inverse map, let's say S, from W to V can exist. Since if you started with W1, it's going, where do I go to? V1 or V2? I don't know how to go back. I'm supposed to go to a unique place. So S doesn't exist. There's no way the inverse map S can exist, since it would have to map a single vector in our picture, which we call W1, in W to multiple vectors in V. And it's going, where do I go? If you now take S and try to map W1 back into V, S is going, I don't know where you want me to go. Both of those could be coming to W1 from the same location. So there is one justification for saying that an invertible map, if it's non-injective, you can't find a map that's invertible. Also, if it's non-surjective, if T is non-surjective, then that means we're not covering all of the domain. I'm sorry, all of the codomain with our mapping. Yes? Codomain is the output. So if we have a surjective map, we're supposed to be able to hit every vector in the output vector space. If it's not surjective, we are not getting to every vector in our output space, vector space, or we're not getting to every vector in our codomain. If T is non-surjective, then there are vectors in our codomain W which are not produced by the linear map T acting on the vectors of our domain V. But the inverse map S going from W to V would have to somehow ignore those points in our codomain, our original codomain, in going back from W into V. But the inverse map S, which is supposed to be a linear map, would have to ignore those elements of W, but that's not allowed. But a map acts on all elements of a vector space, of a space. Meaning in pictures, we might have something going from V to W, and let's say that that now is the range of our linear map T. And we actually might have points or vectors outside of the range of T in W if we have a map that is not surjective. Now, what we want to say is, what's S going to do? S would have to somehow ignore those vectors that live outside the range of T in order to go back effectively to V. And that's not going to happen. Our maps have to use all of, or take all of the vectors in our domain. So that S does not exist again. An S that allows for that ignoring of those unmapped into vectors. What else can we say in terms of this relationship? We also have some earlier results about dimensions of maps when they're injective and surjective. No map to a lower dimension can be injective or surjective. If we go from let's say a domain that's of dimension 5 to a codomain that's of dimension 3, what do we know about that map? Is it able to be injective? Is it able to be surjective? What we can claim is that map cannot be injective because it has a non-trivial null space. If it's mapping 5 into 3. So no map to a lower dimension, 5 to 3, can be injective. So we know we can't collapse or have a dimension reducing map and have an inverse, or for it to be injective. The other point is no map to a higher dimension can be surjective. We can't cover every point if we go from 2 to 6. We aren't going to be able to cover the entire 6-dimensional codomain if we're starting with a 2-dimensional domain, which basically says we need to be mapping between similarly dimensioned spaces. or we see that inverses only exist for maps between vector spaces of equal dimension. Because of those restrictions on our maps being injective and surjective. If it's injective, we can't go decreasing our dimension from domain to codomain. If it's surjective, we can't go expanding from domain to codomain. So we have to stay in the same dimension between our vector spaces. That raises a question. What does this mean, this result, that we have to basically be playing on two equal dimension spaces? What does this mean in terms of a matrix representation of that linear map? If we have an invertible linear map, what does that mean in terms of the matrix representation of that linear map? It has to be square, doesn't it? It has to be n by n, Nevada by Nevada, and that's our answer. The matrix representation must be square. Which, another way of thinking of that is that the columns of this matrix representation of a linear map T, those are T1, TV2, up to TV sub n, are represented by some linear combination of the basis vectors in our codomain. So those are expressed in terms of W1, W2, let's say W sub n. But the only way that those columns can map into M basis vectors in our codomain is for little n to be equal to little n. So the same dimension is true only if n is equal to n, or the number of columns equal the number of rows which says we have a square matrix. Or only square matrices have an inverse. And that now allows us to start talking about vector spaces that look the same. If we can go back and forth, if we can start in V, go to W, and then we can go right back from W back into V, that allows us to basically compare two vector spaces, or talk about what are referred to as isomorphic spaces. two spaces are said to be isomorphic if there is an invertible linear map between those two spaces. And two isomorphic vector spaces actually have the same properties. One result that we can write down from that is Theorem 318, and that is that 2, do you remember what we were meaning by FDVS? Finite dimensional vector spaces. So 2 finite dimensional vector spaces are isomorphic if and only if they have the same dimension. So if we say 2 vector spaces are isomorphic, you can just sort of say, oh, those are similar to each other. They have similar properties, these vector spaces. And one of the main things that those vector spaces share is they're the same dimension. If one is of dimension 5 and it's isomorphic to another vector space, then that also has dimension 5. Now, if we wanted to show that or prove that, what would we need to, or what's one way of doing that? And here, in anticipation of exam number 1, what's maybe a key word in that theorem that you can start thinking about in terms of a proof strategy? So you want to be keyed in on BFF, your best friend. I'm sorry, IFF. If and only if. That means you probably want to show that it works both ways. Statement A implies statement B. Statement B implies statement A. And then you're done. So that if and only if sometimes suggests that maybe you want to show or prove this theorem by going in both directions. So here, let's say need to prove in both directions. So first, let's go ahead and assume that the domain and the codomain are isomorphic finite dimensional vector spaces. What do we know about 2 vector spaces, finite dimensional vector spaces that are isomorphic? By definition, they have an invertible map between them, don't they? By definition of isomorphic, this means there is an invertible linear map T between V and W. But now what do we know about invertible linear maps? It's injective and surjective. So now we can say an invertible map implies injective and surjective. And what did we just say earlier? We said no linear map is injective to a finite dimensional vector space of smaller dimension. Well, we could write that by saying we now know that the dimension of our domain is less than or equal to the dimension of our codomain. The codomain has to be the same size or larger if we have an injective map. And we know if we have an invertible map, we have an injective and surjective map. So now we know one relationship between the dimension of our domain and the dimension of our codomain. We also know that no linear map is surjective to a finite dimensional vector space of larger dimension. That now says that the dimension of W needs to be less than or equal to the dimension of our domain, right? Since we can't go bigger, we know the codomain needs to be dimensionally less than or equal to the dimension of our domain. And being injective says that the dimension of our domain needs to be less than or equal to the dimension of W. Now we just combine those because it has to be injective and surjective, which now allows us to say that the dimension of V is less than or equal to the dimension of W, which is less than or equal to the dimension of V. And since V bounds W on either side, we can now say that the dimension of our domain needs to equal the dimension of W, which is the direction that we needed to prove first. That if we assumed A, our finite dimensional vector spaces, both of those were isomorphic, that's statement A, then that's supposed to imply that those two are the same dimension. And we just showed that the codomain and the domain were the same dimension. Now let's assume the other. Let's assume that we start with the dimensions being the same of our domain and codomain and see if we can now show that the two vector spaces have to be isomorphic. And then we will have gone the other direction. Let's now assume the dimension of V is equal to the dimension of W. Let's now take V1, V2 up to V sub n as a basis on our domain. And W1 through W sub m as a basis on our codomain. Now, consider the following map. Consider the particular linear map, let's say T operating on A1 V1 plus dot 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 plus A sub n V sub n is taken into A W1 plus A sub n W sub n. Whoops, A sub n W sub n. That's really saying TV1 is equal to W1, TV2 is equal to W2, etc., isn't it? So now we've created this linear map T. Where this definition meets additivity and homogeneity. So it is a valid linear map. So we started with dimension of V being the dimension of W. Now we have these basis vectors that are equal in number. We have n of those. We've now created a particular linear map. T operating on a vector V is equal to another vector W. But that right-hand side could be created, or any vector in the codomain can be represented by the right-hand side. Any vector in W can be created through the appropriate choices of the A sub i's. And we know that because the W sub i's are a basis, which means they span all of that codomain W. What can we say then about the linear map T? If we can go to any point in the codomain W, what property does T have? Surjective, isn't it? Now the range of our linear map covers all of the codomain, so T is surjective. Or these TV sub L's covers all of W. Now, because the W's are linearly independent, and we know that because they're a basis of W, the only way for the right-hand side above to equal 0 is to have what for the A sub i's? Those all have to be equal to 0, don't they? If that right-hand side is 0 and all the W's are linearly independent. If all of our w's are linearly independent, the only way that they can equal 0 are for our scalars, which are the a sub i's, to all be 0. So the right-hand side is equal to 0 is for the a sub i's to all be 0. But if all the a sub i's are 0, that actually forces the vector in our domain v to be 0. But this forces the vector in v to be 0 as well. Or that's basically saying now that the null space of T is the 0 vector. The only way for us to have a right-hand side here equal to 0 is if the vector that is being mapped through the linear map T to get to 0 is for that to be 0. And what happens when our null space is trivial? What kind of a map do we have? It's injective. So T is now injective, which we started with the dimensions being equal, and we concluded that that led to T being surjective. It also said that T is injective. So T is injective. And surjective. Which now says it's invertible. Which now allows us, since we have an invertible map between V and W are isomorphic, just by starting with the fact that V and W were of the same dimension. We were able to show that. So V and W are isomorphic. And this is a huge or a big result. That says really that any m-dimensional vector space is isomorphic or has the same properties to, let's say, this m-dimensional vector space R to the m, for example, or C to the n. Yes? So a linear map, we haven't said too much on a linear map in terms of what the domain and the codomain have to be dimensionally. So now I think we have assumed that the scalars are operating on the same fields when we do these mappings with a linear map. So the vectors, you now have to have, a linear map needs to be able to just satisfy additivity in the vector spaces, whatever that means relative to the domain and the codomain. But now let's specialize that even more. I mean, we can always sort of, if somebody gives us an m-dimensional vector space, a 5-dimensional vector space, we could always sort of say, oh, that's isomorphic, or that has the same properties as R5, for example. But sometimes that may add more baggage than we need. We may want to just work with maybe these polynomials that are fifth order or fourth order to give us this R5 dimensional space. It may just be cleaner to work in the underlying vector space instead of saying, oh, I'm going to think about that in terms of R5. But you can make that connection since they are isomorphic. What we want to talk about at the end of chapter 3 is this concept of an operator, which now we're specializing a particular relationship between the vector spaces in our domain and in our codomain, where we're saying now an operator is a linear map from a vector space onto itself, which means now if T is not only a linear map but also an operator, then it's taking V back into V. It maps from our domain's vector space back into the codomain being the same vector space. And we may denote that by the set of all operators on the vector space V as the linear map from V into V. We may just collapse that and say those are now operators on this linear map from V, or associated with V. And in general, the rest of this course is going to be concerned with operators, not so much linear maps, but operators. Except exam 1 will obviously be talking about linear maps, chapters 1, 2, and 3, but from this point on in the material, we're going to be specializing to operators, which allows us to be talking about eigenvalues and eigenvectors, etc. So in general, for the remainder, of the course, we will focus on operators. And these are actually a little less general than linear maps, and that leads to some interesting properties. Let's look at Theorem 3.21. If V is a finite dimensional vector space with T being an operator, a linear operator, now we're mapping from the domain back into itself. The following statements actually imply each other. So if we're dealing with an operator, which means we're going from V back into V, then we can say that the following statements each imply each other. Meaning, 1, suppose T, or that basically means that they're equivalent. T is invertible. T is injective. T is surjective. So if we have a linear operator, now if we have an invertible linear operator, we could say, oh, it's injective. It's one-to-one. Or it's onto. Or if it's onto, it's invertible. Or if it's one-to-one, it's invertible. All of these statements imply each other. Let's see if we can show some of those implications. Proof. In A, let's assume that we have an invertible operator. Well, if we have an invertible operator, we know that if we have a linear map that's invertible, it's injective and surjective, so 1 actually implies 2. So 2 is implied by the definition of this map being invertible. Which was proposition 317. And that then says, therefore, T is injective or statement 1 implied statement 2. Just from the fact that we had an invertible map. What about another implication? Let's say B. Let's assume we start with an injective map, or assume assume statement 2. What do we know about the null space of an injective map? Pardon? If we have an injective map, then what do we know about the null space of that map? It's one-to-one, isn't it? So it can only map the 0 vector into the 0 vector. We can't have a non-trivial null space. So the null space of a map that is injective needs to only contain the 0 vector. If that's the case, remember one of these theorems that we've used or talked about, which is actually Theorem 4 in Chapter 3, and that dealt with this relationship between dimensions. Remember, the dimension of V, the dimension of our domain, was equal to the sum of 2 dimensions. It was the dimension of the null space of T plus the dimension of what? The range of T. But now what have we just said? We now said, what's the dimension of the null space if it's the 0 vector? It's 0, isn't it? So now we have dimension of our domain, V, is equal to the dimension of the range of T. But what's the dimension of the range of T, or what is the range of T if it has the same dimension as V? It has to be N. So now it has to cover the entire thing because we now have an operator which is going from V back into V. So this now says, thus, T is covering the entire codomain, which is all of the range of T. So thus T is surjective, or we've now shown that 2 actually implies 3. And maybe what I will let you do, you can sort of play with that same dimensional equality from Theorem 3.4 to look at how maybe a surjective map implies invertibility. And I'll leave that for you, but that should complete Chapter 3, and we'll quickly go through Chapter 4 or use Chapter 4 results in Chapter 5. So we'll start basically with Chapter 5.